Good morning, everyone. So, welcome to this new session of this Dennis Fest. So, our first speaker this morning will be Professor Alexander Shnirelman from Concordia University, who will deliver his third talk about fluid dynamics.
Yeah. So today I want to touch other subject which is called weak solutions of Euler equations. Weak or generalized solutions. This means the following. If we consider solutions, the fluid flows which are not smooth, then they are not solutions of the Euler equations in literal sense, because the corresponding function can be even discontinuous. Yeah, so we have to replace these differential equations by some integral identities. No, in fact, when we derive the Euler equation or any other equations, physically we start from some conservation laws which relate to finite volumes of material, and then provided our fields, velocity fields are smooth enough, we can go to infinitesimally small volumes and pass to differential equations. So the primary object is exactly weak solution. No example of weak solution of Euler, for example, in the plane. Suppose that here velocity is constant and directed to the right, and here it is constant directed to the left. And on this line, the velocity is discontinuous. So this, yes, please.
So the conclusion of what you said then is that a weak solution is a larger set of things than a smooth solution. But if a weak solution happens to be smooth, it's an actual solution.
If a weak solution is smooth, it is a classical solution. Yes, but there exist weak solutions which have pretty good meaning, which are not smooth. So we have to understand them as weak solutions. So this is a typical weak solution with such a tangent discontinuity.
Constant, those are constant speed.
Excuse me?
Constant speed.
Constant speed, yeah. Yes, constant speed. So here u is 1, 0, u is minus 1, 0. This is a weak solution. But the definition of weak solution looks as follows, the formal definition. Consider the Euler equations, du dt plus u gradient u plus gradient p is 0, and incompressibility. Now let us multiply this first equation by some vector field W, C0 infinity with compact support, for example, and which is incompressible. And the second equation, let us multiply by phi, scalar function, C0 infinity. And then integrate, multiply by this function, this, and then integrate by parts. So we have the following with minus u dw dt. It is from this. Plus, I multiply by this vector field multiply, so I write du dt times w.
What does times w mean?
Huh?
I want you to explain what times w means. Inner product?
Yes, it's an inner product, yeah. Just inner product. Plus u gradient w times u. And gradient p is orthogonal to incompressible field w. This incompressible field, so this vanishes. The gradient p vanishes from this integral. Dx dt is 0. And second, u gradient phi dx dt is 0. So this can be called Euler equations, and this is weak Euler equations. And if u is a vector field satisfying this for any test function w and phi, then this u is called weak solution. Now observe that here we have no derivative of u. Here we have just u and the product of components of u. And w is a smooth function. So we can assume that u is only L2. And this is enough to make sense of these equations. So u can be just square integrable vector field, and if it satisfies all these equations for any test functions w and phi, then u is called a weak solution. Now, again, if u is a priori smooth, say C1, then we can go back and conclude that u satisfies the Euler equations. However, it is a priori there exist much more solutions, which weak solutions, strong solution. Every strong solution is a weak solution, but possibly there exist interesting weak solutions which are not strong solutions. And this is my purpose today, to construct some interesting weak solution of the Euler equation. No, first of all, there exist different, very different weak solutions which are known today. The first really interesting example was published in 1993 by Schaeffer. No, in fact, he said that he worked for at least 20 years on his on this example, so he conceived it long before. It was a very strange solution. It was u xt x in the plane such that u xt is a weak solution, satisfies weak Euler equations, and u is identically 0 for module t more than 1. Yes, and for module x more than 1. So what happened here? No, u is identically 0. Yes, and so this is x, this is t. So u was concentrated in this cylinder. Here it was not 1, not 0. And here it was 0 for t less than -1, more than 1. And outside the unit disk, it was always 0. But it satisfied all these conditions for any test functions. It was very strange. So it looked like the fluid in the plane was immobile, nothing moved till some moment, t -1. Then it, in a strange way, was set in motion without breaking any of these conservation laws. Yes, and then this motion suddenly stopped, and all this without apparently any outside forces. So it broke conservation of energy. It was something very strange, and after that I was unable to understand the details of his construction, and found my own construction of similar example on the torus, which was instead of 65 pages in Schaeffer was only 25. And 2 years ago appeared much better, more transparent versions of Delelis and Shakelichidi, who found a large class of such solutions in all dimensions, and no, they exploited more or less the same idea as Schaeffer's, not mine. And in parallel, some version, then it was Delelis. I think this. Then it was Bronzi. She is Brazilian. No, approximately this time. She is a student, and I proposed her to make a different approach to my example. And today I am going to tell still another idea of such example, not repeating what was done before, which is closer to what I told yesterday. So let me begin with the following notions. It is generalized flow.
Excuse me. Can I ask a kind of structural question before you leave?
Yeah.
Of course, you can apply this process to any equation, multiply by a test function, and try to integrate by parts. But is there something special about this Euler equation that makes this nicer, or is this just a general procedure?
In fact, these guys.
Solution. It's about the
yes.
question about the definition.
Yes, in fact, these guys included it in a much wider class of equations which have a similar structure. So,
is there anything special about the nature of this equation that makes this weak equation have some properties, or is it you can just do it in general? See, I thought nonlinear equations.
It is a particular case of some general phenomenon.
You're not hearing my question.
No.
What about incompressible? What about compressible?
Well,
do you have weak solutions for
and then go one step further. The notion of weak solution, in fact, was introduced, I think, by Riemann for compressible flow. The first notion, because, in fact, this guy, they are shocks. So it's like the first example of etc. So it's a very natural idea for practical problems. Not
But you can do it to any equation.
almost. I mean, I don't know any equation for which you cannot write a weak.
Okay, that was my question. Is there something special going on here?
No, it's not special.
Okay.
I would say the definition is more or less universal of weak solution, but construction can be bound to specific nature of equation. Yes, please.
And I think the idea behind the distribution of Schwartz.
Right, but I always think of distribution theory as being linear theory.
No, yes, you are quite right. So the pathologies appeared here because we use this linear notion in very nonlinear problem.
Yeah.
And so some things escape definition of linear distribution. Yeah?
Okay.
So in fact, we need here some other theory of nonlinear distributions which we don't have. Yeah, that was a question.
The notion of weak solution goes back to Riemann. Okay, it goes back to Riemann. But the continuity for the linear is the distribution.
Yeah.
So here you're integrating with respect to space and time variables to define weak. I'm wondering, is there an intermediate notion of weak where you just have sort of a weak solution spatially for each t or something?
No, in this case, we integrate over the whole space-time. So here is no boundary. Yeah?
I mean, I had the mistaken idea that if you have divergence-free vector fields,
Yes.
that makes sense for L2. You can talk about divergence-free, because that's a linear equation, so it makes sense for any distribution.
Definitely.
Right? And you can show that the Lie bracket of two divergence-free L2 fields is also a distribution in L1, but it is a distribution.
No, it can be not defined.
I can define it.
It is a bilinear operation, so
You can define it. There's a formula for it. Using D star. It's D star U wedge to W, because the other terms in the formula vanish. So I thought that was the reason you could define a weak solution, because the Lie bracket is well defined as a distribution of any two L2 divergence-free fields. They have to be divergence-free.
Mm-hmm.
So you're saying that's not the point. Okay.
Okay, so I want to develop some apparatus to work with weak solutions. So if we have a smooth velocity field, then we can follow the motion of the particles. We can write the following. We can find not only the velocity field but also the flows of the set of diffeomorphisms. So d ft x dt equals u ft of xt. F0 of x is x. So this is the system of ordinary equation which describes the flow diffeomorphism for U smooth. Yeah. If U is non-smooth, but say a priori just L2, then there is no meaning of this equation. No, at least we cannot hope that it has unique solution. So we don't have this correspondence. The velocity field may exist, but the corresponding flow, Lagrangian flow, already does not exist in our usual sense. So we have to restore the notion which replace the Lagrangian flow. So this is what I call generalized flow. So if the trajectories can split and can collide, there is no natural correspondence between the fluid particles and the points of our domain, flow domain. So we have to regard them as different things. So I introduce now the space omega, space of fluid particles. Omega has it is a measure probability space. It has sigma algebra F of measurable sets and probability measure mu. Now, what is generalized flow? Generalized flow is defined as for almost all omega in omega. We have x of omega t in our flow domain M. Yeah, so we have a map x c for any particle or almost any particle of fluid. We put in correspondence this trajectory, this continuous trajectory inside our flow domain M. Yes, and the first conditions which were imposed, it was introduced by Liapunov. The first conditions are the following. Let me write here. First is that the density is constant. This means that for any, say, measurable and any t, mu omega such that x omega t in A is Lebesgue measure of A. So probability for the particle to get inside some subset A is equal or proportional to its measure. And second, that the finite mean energy, integral over omega, integral from 0 to t, x dot omega t square, no, 1/2, dt d mu should be finite. So mean kinetic energy is finite. So these are the general conditions imposed on the generalized flow. So it is, in other words, it is a sort of random walk in our domain M, satisfying these conditions, which, by the way, make it very different from what is popular in the stochastic analysis, sort of Brownian motion. So Brownian motion does not satisfy this. Next goes, so now we can impose some other conditions. It depends on what sort of problem we consider. So the generalized flow is not some fixed thing. It is a concept which gives a framework for very useful framework for discussion. So I impose the first condition.
It's not really fair to say Brownian motion doesn't satisfy that, because it doesn't satisfy it. However, the physicists build an ansatz to construct Brownian motion where they use the energy. It's just that when they take their limit, you're just on the border of that being infinite. A random path is approximately whole or continuous over a path. trying to satisfy that, it just doesn't.
You can stretch it, but in fact it is has nothing to do with Brownian motion. So
But I mean,
no, okay.
the motion is constructed using that interval. It's unfair to say it has nothing to do with it. It's just
Yeah, there exists u xt in L2 such that x dot omega t equals u x omega t t for almost all omega t. So the last means that the velocity with the probability 1 depends only on position. It doesn't depend on which particle. So I mean that we can consider generalized flow such that, say, half of the fluid is moved one direction and the other half in the same volume in the second direction. So the velocity is not defined everywhere. Velocity field. Velocity relates to the particles but not to the points of space-time. And this makes a relation between position and of the particle and its velocity. So I impose this condition, and now I consider the following problem. So all my construction is variational. So I start from the following problem. Given two diffeomorphisms, two fluid positions, say F and G in D of M. So we have two diffeomorphisms preserving volume, as I explained before, and find a flow or trajectory Ft, t from 0 to 1, such that F0 is F, F1 is G, and integral from 0 to 1 integral over M Ft dot of x square dx dt, it's the action, is minimal. So we have to minimize this action. Yes? So it is a variational problem, and if we manage to find such a flow, we found geodesic connecting to position. Yeah? So it is what we would like to have. So it is a solution of Lagrange and Euler equation. But the problem is whether such minimum is achieved. Yeah? Now, I have proved long ago that in three-dimensional case, there exist pairs F and G such that the minimum does not exist. So we can have minimizing sequence, but it does not converge to some smooth flow. It converges possibly to some generalized flow. Yeah. So in n equal 3, no interesting solutions could be, of a classical solution could be constructed this way. In a two-dimensional case, the problem is still open. So the most probable that in two dimension we have always, usually in general, we have discontinuous minimizer. So this minimizer, even in 2D, is discontinuous. So it is, there is no continuous solution. So it is a bad problem, But nonetheless, we will use it, consider this problem, because it is useful to construct a weak solution, at least in two-dimensional case.
Before you erase the weak solution, so suppose you have a weak solution, u of xt. Is there, one could ask, is there a generalized flow that underlies it?
So I would say, if I say, okay, I will not erase it for a while, and I will instead of constructing classical solution, we can try to construct generalized solution of this variational problem. Namely, we can consider the problem. Find a generalized flow, omega f mu x. So construct the omega and construct these trajectories such that it satisfies all the three conditions which are written here, and the following additional condition. If x of omega 0 let us do the following. To be sure, let us write f is identity map. Because the fluid is homogeneous, we can take the initial position of fluid as reference position, and all other positions obtained from this. So to work with it is easier to work such that x omega 1 equals g of x omega 0 for almost all omega. So if we start at some point, then we almost sure finish at the point defined by diffeomorphism G. And integral f t dot omega t square dt d mu is minimal. So instead of considering the classical flow, which can
X dot there, not F dot, don't you?
Excuse me?
X dot, not F dot.
X dot. Instead of considering the classical flow, smooth flow, we consider just generalized flow. It turns out that this problem always has solution, which was proved by Brenier. And next solution exists. So if this generalized flow satisfies condition 3, this condition. Condition 3, that there exists some velocity field. So we have no intersection. Then we have velocity field u of xt is a weak solution. weak solution of Euler. So if we manage to find minimizer which such that the different trajectories do not intersect transversally, then this is a weak solution. Now the question is how to establish it, because this fact apparently does not depend on our will. It holds or it does not hold, depends on the problem. To this end, I want to introduce a little bit more structure here. Structure of a braid. So we are in two-dimensional case. So consider the our domain M, where the flow goes, and the third coordinate T.
This is result applies in dimension 3, right?
Excuse me?
Riemannian result applies in dimension 3.
No. What I'm telling is only two dimensions.
This result.
This result, yes, in any dimension, but it is conditional result, so it is in some sort empty. Yes. So here we have some if, and in dimension 3, this if means that doesn't happen. In dimension 2, it helps if I introduce some other structure. Yes. So consider first smooth flow. Consider flow Ft of x smooth flow. Suppose we have smooth flow. Then consider trajectories of the fluid particles here in this cylinder. For different initial points, we have these lines which go from bottom to top and do not intersect one another. So they form really what can be called a braid. Now, in this case, it is braid consists of continuum of lines. So it is continual braid, but why not? Continual braid. Excuse me?
They cross.
No, for smooth flow, they don't cross.
Oh, smooth, yeah.
Yes. Yeah, for smooth flow, they don't cross. And now I introduce the notion of generalized braid. No, I will also call it braid. So let us take this braid, Ft, as a reference braid. And now I give a definition. A flow, generalized flow. No, let's call it G. G is the tuple of all these components of generalized flow.
Generalized flow is 1, 2, and 3. What's the definition?
Generalized flow is currently 1, 2.
Oh, 1, 2.
1, 2. 3 is additional. The generalized flow G is called braid, which is weakly isotopic. To this braid, this braid is B0, defined by this flow. Weakly isotopic to B0. If the following is true: first, for almost all omega, x omega 1 is G is F1 of x of omega 0. This means that if we start at the initial point of some line of braid, smooth braid B0, then we end at the final point of this line. So the lines of the generalized flow, trajectory of generalized flow G have the same endpoints with probability 1. Same endpoints as the lines of B0. And second, if omega 1, omega n are, they independently chosen random trajectory, independently chosen particles with each with a probability distribution mu, which is given. So there's independent particle, then the lines x omega 1 t, x of omega n t form an n braid isotopic to the braid, say ft of x omega 1 0, ft of x omega n 0. Yeah, so if we take any at random any particles and consider their trajectories, then they form in the cylinder a braid which is isotopic to this reference braid B0 with the same endpoints. So this is next condition. And now I pose the following problem. For almost all for almost all sets omega 1 omega n, with probability 1, yes, of course. And now the problem. Find a generalized flow which is a braid weakly isotopic to B0 given braid, and such that its action is minimal. So beside the general conditions of generalized flow, we imposed one more condition, that this generalized flow is in fact a braid isotopic to a given braid. And the theorem is that first, such braid exists. Yeah, so we can take the minimizing sequence and not only find the weak limit which gives such that this action is minimal, but also this weak convergence preserves this topological condition.
GF exists. Braid equivalent to that.
Braid, yes, no, B. GF, no, GF because such a GF, yes. GF exists. And second, GF is a braid, isotopic to B0. And the third is that this braid, GF, has a definite velocity field. U of xt. Yeah. So it is the third condition which was written here, that for almost all xt, corresponding velocity of the particle depends only on position and time moment. And the consequence is that u xt is a weak solution of Euler equation. So this way yes, please.
So in particular, these points generically don't touch each other with probability.
With probability 0.
Probability 0.
They touch.
Don't with probability.
Yes. Almost. Yes.
So your measure.
Yes. No. Let me just show why it is true in one example. What we are fighting with. So we can consider the following. Suppose this is our domain. This is our cylinder. Suppose that half of these lines go this way, so they spread a little in the other half. The lines are going this way, yes? And here the lines are going this way. So part of the line, some lines are do in...
Draw it. I mean, as you explain it, you can't stand in front of it because I can't see.
I'm sorry. Okay, so suppose we have the following picture. This is our cylinder, so this is our domain M. This is T. And now let us take this plane, for example, plane section, and suppose that some line in this section behaves like this. And some line in the same section, which starts here, behaved like this. So they have two intersection points. No, first of all, and the same happens in all parallel sections, vertical sections. Yeah. So what does it mean? First of all, if we choose by random two lines, they are with probability 1 in different planes. So they don't intersect. Yes? And second, if you consider these two braid made of these two lines, yes, then it is isotopic to parallel braid, if they are in different planes. Now, if they are in the same planes, we do the following construction here. We replace this by... No, let me draw this plane only. Let us replace this by this trajectory. Yes, reconnect it. Yes. No, it is not a great deal because here we have a next line. But let us reconnect here as well. Yeah. So we have here some reconnect operation, and this reconnection does not change the topological type of this braid. Yes. No, here it is obvious, but I can prove. No. No, if we reconnect here and reconnect here, it will come to the same endpoints. Yes. And so if we consider the sequence of these reconnections and make them denser and denser, these moments of reconnections, then in the end we replace these lines by the resulting lines will be parallel. Because in between the line will go like zigzags. Yes, and these zigzags.
What do you mean?
In fact, let us draw this plane, yes, and reconnect the lines at their intersection with this plane, transversal plane. So the line come here, reconnect here, Yeah? Then we consider another plane, and now we consider this plane which becomes denser and denser, so they become everywhere dense. Yeah? In the limit, we have some additional property that the weak limit of such generalized braids is a generalized braid. So this property is stable under weak limit. It's also true. So weak limit first will have smaller energy because the limit of the zigzags will be just straight line or some line with smaller slope. And the topology will be preserved. So if we assume that here are some intersections, then we can remove them, reducing the energy. So this is the general idea. Okay, so we found the weak solution in this case. Now, I started with a smooth braid.
No, in this picture, what did you start with?
This picture I started from generalized flow, which is not which is a braid but does not have the velocity field, because we have at almost every point we have at least two velocities. Yes, and then after a series of such transformations, we have other braid, other generalized flow, which is possibly still not have this unique velocity field, but definitely has smaller energy. So every time when we have the generalized flow which does not possess this property, we can transform it using these reconnections into other which has smaller energy. Yeah? By the way, here I again use this lemma which I mentioned yesterday, that if we have a sequence, non-increasing sequence, with indices all countable ordinals, then it stabilizes since one moment, because here the ordinary integer indices for this sequence can be not enough. I cannot control how much I can reduce the energy at every step. But if I go to this transfinite indices, then it's enough to reach the minimum, to reach a situation when I cannot reduce it anymore. So I reached a good flow, which unique velocity field. And now the last thing, how I can improve or change this construction. Is the following. I call it folded braids. Yes, it's another object which looks as follows. No, what is finite folded braid? So consider our cylinder. Suppose we have a line which goes from top to bottom, reached some point on the bottom of this cylinder, and then returns to the top. Consider other line of this sort. Now consider all the lines such that they have fixed endpoints on the top, and in between they reach the bottom. So have two parts, and don't cross each other in no points. Yeah? And consider different isotopic classes of these lines, of these sets, tuples of lines, say n lines like this. This object I call folded braid. Yes. So and now I construct first.
Every point on the bottom has two trajectories coming into it.
No, if it is a finite folded braid, then we have just finite number.
Okay.
Yes, but I construct infinite number, continual folded braid. This means that all the cylinder is filled by these lines, and the different lines don't intersect with probability 1. And now I do just in this same spirit, I find the minimizing, so such a folded, continual folded braid, which minimizes the energy. Yes, and the same way I prove that it exists, and this minimizer has unique velocity field, say V xt, yes, which is a smooth solution. And now the last thing is the xt smooth weak solution. And the last thing, that when we go to 0, t goes to 0, this vector field V goes to 0 weakly. This means that I would write it in the following sense. So V goes to weakly goes to 0 as t goes to 0 in the following sense. If we take any test function W, vector field, W is test field, and consider integral from 0 to, say, epsilon. Oh, I'm sorry. Let me write here. Integral from 0 to epsilon, integral over our domain M, V times W dx dt, yes, 1 over epsilon, goes to 0 as epsilon goes to 0. This means that this, by definition, the problem is that L2 vector field has no value on the bottom or on any surface. So we have to introduce some weaker, some integrated form of weak convergence. So this definition of weak convergence to 0 for any fixed smooth W, mean value goes to 0.
You get such a thing assuming what? What did you start with?
We get it assuming that V is the velocity field of minimizer of the action or of the mean energy for the folded braid.
For a given mapping? For what? For given what, though?
Given the isotopic class of this folded braid. So I first constructed some initial braid, which is a result of some flow. So I construct this flow, yes, by hand. And then I take it as a reference braid and consider all the folded braids which are isotopic to this. Yes, and then I minimize the energy of the braid in this class. So the minimizer exists, and for minimizer there exists a unique velocity field, and this unique velocity field is exactly a weak solution, such that it goes to 0 weakly.
Right, but the map from top to bottom is a 2-to-1 map.
Yes.
So not a diffeomorphism.
It's not a diffeomorphism. Yeah. So this map is, in my case, easy to understand. It is the following map. We take the square, no, we consider it in the square. We take the left part of this square and stretch it on the whole square, and take the right part also stretch on the whole square. So it is 2-to-1 map. Yes. So what we achieved this way? We achieved a velocity field. What does it mean that the velocity field V goes to 0 weakly? This means that its Fourier coefficient goes to 0 separately. But the sum of the squares of Fourier coefficients stays constant. Yeah? This means that the energy goes to higher and higher harmonics. This means that this velocity field becomes more and more oscillating. It's exactly what I showed in my movie. We started from velocity field, which had some small scale structure, collection of small vortices. Yes? And here this situation is pushed to the extreme, that the size of initial structures is 0. Yes? And so it was 0, but for any positive moment it's no more 0, it grows. So here we have an extreme case of inverse cascade when the size of the structure, of the scale of the flow, grows from 0 to non-zero. No, that's it. What remains unclear is the meaning of this weak solution, physical meaning, because it is really non-regular flow, and it would be very good to find a smooth solution of Euler which is close to this singular solution. No, it is not done, and I don't know how to do it. So it stays as isolated result. But how it is connected with the mentioned in beginning results of Schaeffer and so on? It is connected in the following way. So it is X, it is T, it is our domain. Here we have this solution defined, V, xt. And let us continue it with 0. Then this will be defined for all t, and this is a weak solution, including this plane, t equals 0. And so we have example of weak solution which is 0 for negative t and non-zero for positive t. And something happened at t equals 0. So what happened at t equals 0? It looks like the fluid received some kick at this moment. Yes, some force which pushed it, and then after that the fluid flow developed by itself. But this kick is not perceived by multiplying by a smooth function and integrating. So this initial force is orthogonal to all smooth functions. So it is not a distribution. It's concentrated at infinitely high frequencies. Yeah, so it is some new object which has, for today, has no true meaning. We see the consequence of this. So we construct this big solution, and the best way to define it or to understand is to take this weak solution as a sensor. Yes. So in fact, what is the distribution, the meaning of distribution? We define some class of sensors or functionals which are applied to our object distribution, measure some characteristics of this. Yeah? So here we have also some sensor, namely the fluid. What we are measuring is the result of action of this force on the fluid. Yes? And this is very nonlinear sensor, and it feels this force. Linear sensor will not feel it. Yeah, so this means that there should be something like nonlinear generalized function or nonlinear distributions and possibly many different classes of them. But this theory is completely absent. So thank you for attention.
Any questions or comments? Dennis?
If you wanted to use this example, could you flip this example over and get a shaper example?
I could do it.
Just do it. I mean, just take it now.
No, but I cannot do it together. I can change time direction here, but I cannot join this and the overturned example.
Take them together.
No, at least I cannot do it right now.
Okay.
Yes, but possibly it is not so necessary. It is a more sportive interest. I want just to show here that at least half of this example can happen. But the reason, in fact, the reason is the same. So in all examples, in Sheffer, in my examples, the reason is the presence of outside forces. But these forces are orthogonal to smooth functions. Yeah? So it is the lack of sensibility of this sensor.
More questions?
Yeah, I still have a question. When I asked my question before, you answered the converse to the question. What was the question? Oh, yeah. Suppose you take a weak solution, but like Leray, as I recall, that it's smooth at most times. So you start with smooth initial condition, take a weak solution, and then even in dimension 3, right? And then you have it's smooth for most times.
The one-dimensional measure of moments when it is not smooth is 0.
Yeah, right. So you sort of have these smooth things, and then if you take all the bad places and saturate them in time, it still has measure 0. Because so then there is a generalized flow running through there.
Yes.
So that means it's not true what you said that.
Yes, but that is.
Wait a minute. Let me finish my sentence.
Yes.
In D equals 3, you said weak solutions don't have generalized flow. So I'm claiming every weak solution in Loray's sense has a generalized flow.
Because
you saturate the bad places, they have measure 0.
Yeah, because they are better.
Yeah, but you have the viscosity. This set of measures of solution, what makes it of measure 0 is that you have the viscosity.
Oh, that's true. It's not
The
going
viscosity, yeah. And here.
This is. No. Oh, that's what makes it. But still, it is a weak solution of Euler's equation.
Then you don't.
Then you don't know the best time thing. You're right. Okay, sorry. I was remembering incorrectly. Okay. Thank you.
In this example, in the Sheffer solution, what happens with energy at t bigger than 0? So initially it's not conserved, but then.
I think it was not conserved all the time. So it did not have the interval where it was a classical solution. In my example, the set where the outside force actually acts is of measure 0 in time line, yes? So almost everywhere it is a smooth solution. Yes, in Sheffer's it is more spread over the time. But the idea is more or less the same. So we take some non-solution, so that there exists outside force, and then we somehow move these forces, reconstruct solutions so that the forces are moved to some set of measure 0 in xt. And then they are not perceived by these smooth test functions.
And can I think of this physically that we have some, for example, vibrational modes of molecules macroscopically, and then somehow these vibrational modes in the collisions go into microscopic motions. And therefore, even at hydrodynamic, in the fluid dynamics level, I see the energy changes, but it actually comes from microscopic degrees of freedom.
Yes. Yes, it is close to.
In dimension 2, when you're constructing these weak solutions, so since the braids are not colliding, does that mean that the for almost every point you don't have collision?
Yes, almost every 2 points.
Yeah.
We have no collision.
So I guess I have some ill-posed questions. So you explained that. So in your example, when you go down, then somehow energy is pumped from higher scales, from smaller scales through to higher harmonics.
No, when you go to 0, t goes to 0, the energy goes to higher harmonics.
Higher harmonics.
Yes.
So you pump energy from bigger scales to smaller scales.
Yes.
Is there some self-similarity in this process?
It is possibly in this example it will be self-similar, but in fact the self-similarity is a crucial thing here. If the process is self-similar, then the size of the vortices should grow linearly in time, because it's the only possibility, if we consider the parameters and dimensions, the only possibility is that the size of the structures grows linearly. And in 2D, yeah. But in the numerical experiments, I found that it grows, there are some power law, but definitely not linear. Yeah, and it grows slower. Yeah, and so what happens is still unclear. So it is one of many things which go with adjective anomalous. So anomalous. Here anomalous self-similarity. So maybe it's not self-similarity at all. So there are some hidden dimensionless parameters which enter here, which we have to find.
So, I mean, I like this generalized flow definition. So, do the trajectories often not hit each other then? Does that follow because you have the vector field, or does it not follow? Just from the definition, satisfy 1, 2, and 3.
I think this means that for almost all, no, velocity field can be a priori is non-smooth, so they can merge without collide.
Yeah, you can have any.
Yeah, and I think that in 3D it is a crucial mechanism of, say, energy dissipation. This collision of particles without collision, merging without collision. Yeah, and the particles can meet one another without collision. It means that the velocity is the same. Yeah, because the velocity field is say Holder. Yes, and in 3D. This may explain the energy dissipation, yes, and this Kolmogorov law 1/3, yes, and this Anzager conjecture and so on. In 2D, nothing like this happens, so the different particles simply almost sure don't collide, don't meet.
So one last thing. So just to, I'm trying to remember something.
Yeah.
So in 3D, thank you, said that if you have viscosity, and you consider weak solutions of the Navier-Stokes equations, you have one more term over there, then do you agree then that there are generalized flows corresponding because of this
sure.
point? So then they are.
There are
So you have generalized flows that describe weak solutions of the non-obvious Stokes equation.
Yes, yes, it's even better.
More questions? Okay, so let us thank the speaker.
Very nice.
Thank you.